Welcome back. In this lecture, we're going to discuss feature matching. But first, I'd like to welcome you to more or less the unofficial halfway point of the course. So far, we've learned a lot of technical syntax, but we haven't really been able to apply it to more complex computer vision applications. This is now the point in the course where I like to say we can begin to do quote-unquote cool computer vision applications, things that are really applicable to real-world situations. So from now on, we're really going to be focusing on using our technical knowledge and syntax skills with OpenCV to create programs that are directly applicable to realistic situations. We had to kind of eat our vegetables first, learning about things like edge detection and image processing and just video basics, but now we can really focus on some of the more complex and advanced algorithms that OpenCV contains that are directly applicable to things like real-world images. And we're going to begin this by talking about feature matching. We've already seen template matching to find objects within a larger image, but it required an exact copy of the image to be within the image you're looking for, such as when we were looking for the dog's face within the larger image of the dog. Often in real-world situations, you're not going to have the exact picture of that dog's face. So what we're going to do then is move on to feature matching. And what feature matching does is it basically extracts defining key features from an input image using a lot of the techniques that we've already learned, things like corner, edge detection, and contour detection. And then using a distance calculation, it's going to find all the matches in a secondary image. And what this means is we are no longer required to have an exact copy of the target image be within the secondary image. So going back to that dog example, I can now get some sort of generic picture of that dog's face looking to the side, and we can then use feature matching to see if we have some sort of likely feature match in a larger image. I no longer need that exact template to be there. So here's another example of that. On the left-hand side, we have our target image that we're looking for. And notice here, it's just a box of some sort of pre-processed food. And on the right image, we have the actual image that we're searching. Notice that the box is rotated, it's not the exact image, and with feature matching, we can actually link up and see key features and then link to where they match in the secondary image. We no longer need to scan, as we did in template matching, for an exact match. This means this is a really powerful technique for real-world applications where you're only going to have a base image that is not an exact copy of what you expect to see in the secondary image. And we're going to be checking out three methods, the first being brute force matching with ORB descriptors, the second being brute force matching with SIFT descriptors and a ratio test, and then the third one being the FLAN-based matcher. What we're going to be testing is just a generic serial image and seeing if we can find its matching box in a real-world image of the serial aisle. Okay, let's get started. All right, here I am at the Jupyter Lab. I've opened up a new notebook and I went ahead and copied and pasted from the feature matching notebook these import lines that we're going to be using, as well as this display function. Notice the display function already has the CMAP default as gray, so we'll be using this to show the images a little larger. First, let's go ahead and read in the images. The first image we're going to call Rhesus because it's a Reese's Puff cereal box. So I will say CV2 image read, data, and then if you start typing out Reese's, you should see Reese's Puffs.png and pass in a 0 so we can read it in as a grayscale. This is the query image. So we're going to be essentially asking for where it's matching in the secondary image, our target image. So if we scroll down, here we can see the box of Reese's Puffs. You should notice that it's not really a photo of a box of Reese's Puffs. It's an actual just kind of printout of the front of some typical Reese's Puffs. So that's what's really nice about this method. I don't need an exact photo or an exact template of what I expect to see in my target image. So let's actually take a look at the target image. We're going to call that image cereals, CV2, image read, and we'll say data. And if you start typing out many, you should see many cereals.jpg. Pass in 0 there. And then let's display what cereals looks like. And here is the cereals. Notice this is actually a real picture of a cereal aisle. And we have tons of different cereals. Some of them, the boxes are a little crooked. They're not exactly angled exactly towards the camera. So they're not, and none of them are actually front facing in the exact same way this image is. And if you look over here on the bottom left, this is the Reese's Puffs cereal box. You should also notice that it's not exactly the exact same cereal box. If we come back up to this original image, this one here has family size at the top of the Reese's Puff cereal box, and this is just a normal box of Reese's. It's not family size. So keep in mind, some of these other boxes do have family size on them. So Lucky Charms and Cinnamon Toast Crunch and Cheerios, these all say family size at the top of them. So that may affect our feature matching. We may get some matches on the family size, but then we get some matches on this Reese's Puff cereal as well. So we'll be exploring all of that through the 3 different methods. The first one we're going to do is called brute force detection with ORB descriptors. And the first thing we do is we actually create the detector. So we will say ORB is equal to CV2, and then say ORB underscore create. And this is now our detector object. And what we do is we find the key points and descriptors off of this object. So we say ORB dot, and then start typing out detect. And if you tab autocomplete, you want detect and compute. And we're going to pass in Reese's, so the image that we're looking for. And then the second parameter we're going to pass in is none. So it takes in a possible mask. We're not actually masking anything here, so we're going to say there is no mask. And this returns back 2 things, key points, and then their description. So if you take a shift tab here, it'll detect key points and computes the descriptors. So those are the 2 things it's returning here, which we will call KP1 and descriptors as DES1. We're going to copy and paste this and do the exact same thing, but for cereals. And then we'll change these from KP1 to KP2 and DS2. All right, so all we're doing here is we created this detection object which detects and computes features, and then we ran it on both the Reese's and cereals, essentially the target image and the larger secondary image. Once you've done that, it's time to create the matching object. So this is brute force matching. So it's essentially going to see where are the most matchings taking place. So we'll say BF for brute force, and then we say CV2, brute force matcher. And then one of the arguments you can provide here is, and actually it's not detailed in the docstring, is the actual way it's going to detect those matchings. And we're going to use the default, which is CV2 norm underscore Hamming. And then we'll also specify cross check equal to true. So essentially just a bunch of default parameters here. And then what we have is we can actually check where the matches occur. We will say matches is equal to BF matches, BF match, and you can tag autocomplete to make sure that's correct. BF match, and we're going to pass in the descriptors. We pass in descriptors of set 1 and descriptors of set 2. So now we have our matches, and then we're going to sort them in order of their distance. Lots of different ways you can do this. A really common way, and you see this in the documentation, is to use a lambda expression along with the sorted method. So what they like to do in the documentation is state that matches is equal to sorted matches, where key is equal to lambda x colon x dot distance. So what does that actually mean? Sorry, it's distance, no s there. Well, let's take a fresh look at this matches, what it actually is. They are a bunch of specialized match objects. And if we take a look at just one of them, so let's take a look at a single match here. So we'll say matches 0, and then take a look at a single match, hit dot, and then hit tab, and you'll see that they have a bunch of attributes. They have a training index query, but more importantly, they have this distance attribute. And this distance attribute essentially clarifies how good of a match it was. So the less distance it has, that means it's better of a match. The more distance it has, it essentially means it's a worse match. So what we can do is we can actually then sort these by distance. You could do it with a for loop, so just going around calculating, but this is kind of a clean one-liner way of doing that. So instead of manually checking the distance and then appending it to a fresh list, what we can do is just call it the sorted, pass in the matches, and then pass in this keyword on sorted of how we actually want to match them, or sort them, I should say, and we're going to sort them by that distance attribute. So now that we have our matches, these matches are now sorted by their distance attribute. Then we're going to say Reese's matches is equal to, and we actually have a convenient function called draw matches. So given these match objects, we can then draw them. So we will say Reese's, and then we provide KP1, the key points on Reese's. Then we say cereal, make sure you spell that right, and then say the key points 2 for the cereal. And then you can provide all the matches, but if you actually check the length of the matches after you sort them, so we're going to say check the length of matches. There's 265 matches. That's probably too much to visually display, so let's just choose maybe the first 25. So we're going to index matches starting from the beginning all the way to 25, essentially just slicing a piece of that list for the matches. The next parameter we're going to provide is none, because it's essentially asking if you want a mask there. We don't want a mask. And then finally, we'll say flags and set that equal to 2. That essentially defines how it's actually going to draw the matching. So go ahead and run that. And what's really nice about this function is it automatically then sticks together both your target image here that you're querying and then the secondary larger image. And then it's going to draw lines of where it thinks it found matches according to this detect and compute. And you'll notice this one actually doesn't do that well. We'll see some other ones in just a little bit that perform much better. But we're going to say Reese's matches, display that, and here you go. So here are the top 25 matches of features. You can see right now that none of them are very good. In fact, none of them actually even point to Reese's Puffs. So this sort of brute force detection with ORB descriptors doesn't always work, especially if your image doesn't really look like the target image or the image that you're querying. And there's a couple of problems with our image. One is that we have this family size, which isn't even present in the box of the other one. And then the other issue is that it's a little distorted here because it's twisted a little bit and it's on the bottom. Plus, we have a lot of other objects in this picture that look very similar to the target image. So for these sort of tasks, we're going to need some more sophisticated methods of feature matching. And we're going to set up those two much better methods in part 2 of this lecture series. So coming up next, we're going to check out brute force matching with SIFT descriptors in the ratio test and the FLAN-based matcher, which will be able to detect the match over here on this Reese's Puffs box cereal. We'll see you at the next lecture. Welcome back. Here we are where we left off last time. Last time we tried this ORB match detector and it didn't do a very good job. In fact, it kind of got confused given how similar the other cereal boxes were to the Reese's Puffs cereal. So now what we're going to do is use SIFT descriptors, S-I-F-T. And SIFT stands for Scale Invariant Feature Transform. And it does really well when you're dealing with image sizes that are at a different scale. So notice this Reese's Puffs cereal box, it's actually much larger than the cereal boxes that are found in this target image. So that could also lead to some confusion when trying to match up features. So this SIFT descriptor can account for that. And the way this works is we first start off by creating a SIFT object. We'll say SIFT is equal to CV2, and then we call X features 2D dot SIFT underscore create. And then once we've done that, just like we did before, we're going to find the key points and descriptors with SIFT. So we'll say KP1 and DES1. So the key points and descriptors, SIFT, and we will detect and compute Reese's and then none. And I'm going to copy and paste this because it's the exact same for the other one, except it's going to be cereals. All right, so nothing different so far. We've done the same thing as we did last time. We created this object, and then we're going to detect and compute where there are actual description matches. Next up, we're actually going to calculate those matches. So now that we have descriptors for each of them, we want to compare them. So we're going to do this by brute force. We'll say CV2, BF matcher, and then we're going to calculate our matches in a slightly different manner. We're going to do the following. We'll say from that brute force matcher, call KNN match. And what this does is it takes in two sets of descriptors and then a value K. And if you check out the documentation, what it does is it finds the K number of best matches for each descriptor from a query set. So right now we have DES1 and DES2. And if we take a look at these and then let's show what one of them looks like. these are essentially just descriptors of where it found features. So what we're going to do is, given these two set of descriptors, I'm going to use KNN match to find the top two matches. So again, we're finding the K best matches for each descriptor from a query set. So we're going to have two matches for each of these descriptors. So let's run this and then take a look at what matches actually looks like. So matches, notice they're pairs. There's the first match and then the second match. So this first match is a better match than the second match. And if we asked for K is equal to 3, then we would have the third best match. And we could keep on going. So right now, this first column, all these values, that's the first best match. And then the second column is the second best match. And what we're going to do now is apply a ratio test. In general, just intuitively, you could think that if this first match is pretty close in distance to the second match, then overall, it's probably a good feature to match on. That being said, if you have a strong match in the first column, and then the second best match is actually pretty far away in distance, then overall, this entire descriptor is probably not a very good feature to match on. And we're going to apply what's known as a ratio test to actually check for this, to check if these two matches are relatively close to each other in distance, and then we can think of this entire descriptor as probably a good match. And the way we do that is the following. I'm going to keep matches there so we can reference it. I will create an empty list called good, and this is going to hold my good matches. And I will say for match 1, comma, match 2, in my list of matches, remember I have pairs of matches there, I'll say the following. If match 1 distance is less than 75% of my match 2 distance, then I actually probably have a good match. So I will say good append. And as a list, notice here the brackets, I'm going to append match 1. So what this is saying is if match 1 distance is less than 75% of match 2 distance, then descriptor for that particular row was a good match. Let's keep it. And keep in mind, I'm just keeping one match. I'm keeping the first best match, but I am comparing it to the second best match for that descriptor. If these are off by a lot, so if this is greater than 75%, then it's probably not a good match, and I'm just going to toss it away. So this is called a ratio test, because we're essentially taking the ratio of match 1 to be less than 75% of match 2. And in general, keep in mind that less distance means a better match, because we're using some sort of distance metric to evaluate these matches, and the greater the distance, the poorer the match. The less distance, that means the better the match. So we'll go ahead and run this. And now if I check out my list of good, then I have a list of all the good matches. So let's take a look at the length of good. It's 78, and let's take a look at the length of matches. That one was 1,501. So we can see that we actually had a lot of poor matches that we ended up tossing away. And now we're left with the very best matches, about 78. Okay, so now it's time to actually draw these matches and see how they performed. So we will say sift matches. And just like we did last time, we'll say CV2, draw matches, except this time we'll say draw matches KNN, because that's what we used here in calculating these matches. Draw matches KNN, and then same parameters as before. We'll pass in Rhesus the key points for that one. We'll pass in serials, the key points for serials, and then pass in my list of good matches that I already filtered. And we'll say none for mask, and then say flags is equal to 2, so we get the same drawing style as last time. Run that, and let's display that image. We'll say display sift matches. Run that, and you'll see that it performed much, much better than our previous feature matching. It was now successfully able to find where Rhesus Puffs was in the actual serial aisle. Notice how many features we matched here. What's also really interesting is you notice that the family size features here were also well matched to the family size showing in that Cheerios picture. So if we take a look at the original picture up here, So this is the cereal aisle. Notice that family size is actually quite visible here in Honey Nut Cheerios. However, it's missing in this Reese's Puff cereal. And our target image here had family size in it. So that means it actually found the match in that Honey Nut Cheerios. So keep in mind, if you have many similar images, it could still be an error in the actual matching. But as we can see, most of the matches are actually really well detected onto that Reese's Puff cereal. Okay, so that's SIFT descriptors with an additional ratio test. Now what we're going to do is a FLAN-based matcher. For the FLAN-based matcher, we're first going to show you how to grab the matches, and then we're going to introduce a more complex parameter drawing mechanism, essentially just a dictionary that allows you to draw only the clear matches, but yet show all the points where it did find a feature to possibly match on. It's going to be a very similar process to what we just did, and in fact, the results are also going to be quite similar. So let's start off. We're going to end up saying SIFT is equal to CV2, X features 2D, and we'll say SIFT underscore create, just as we did before. Then again, using SIFT, what we're going to say is essentially the same as we did last time. In fact, I can copy and paste the commands. It's just this key points and descriptors, 1 and 2. And then we're going to copy and paste those in. And now what's different is we need to define the FLAN parameters. So FLANN. FLAN means fast library for approximate nearest neighbors. And it's actually going to be much faster than the brute force methods, but it's not going to find the best possible matches. Instead, it's just going to find general good matches. Now, you can play with FLAN's parameters that we're about to show you in order to try to increase the precision or the quality of the matches, but that comes at the cost of slowing down the algorithm. So just in other words, FLAN is much faster than brute force matcher, but it only finds approximate nearest neighbors, which is good matching, but not necessarily the best. Okay, so let's go ahead and show you the parameters, and we're going to be using the default parameters. So the way we can construct this is we say FLAN, and we'll say FLAN underscore index underscore KD tree, and set that equal to 0. It's also going to take in some index parameters. We'll say index params is equal to, and we're going to create a dictionary just by passing this into the DICT dictionary algorithm. Will be set to that FLAN index tree, KD tree, and then say trees is equal to 5. So I would encourage you to use these default parameters, and then you can kind of play around with them, see if adding more trees helps. But again, the more you mess with the parameters, the more you slow down the algorithm. So this is really just meant for fast detection, especially if you have a really large image or a large number of images. Then we'll say search parameters is equal to dictionary, and we'll set checks equal to 50. It's up to you how you like defining dictionaries. You could also have just done this with something like this, where we say checks 50. So again, we're just using a dictionary here because it's a little more readable. Okay, so we have our parameters, and then what we'll do is say FLAN is equal to CV2, FLAN-based matcher, and we'll pass in those index parameters as well as the search parameters. Run that, and now we can actually grab the k nearest neighbor matches using this FLAN object. We'll say matches is equal to FLAN KNN match, and then pass in the descriptors DS1, DS2, and we'll set k equal to 2. And we're going to do a very similar ratio test as we did before. We will say good as an empty list, and we'll say for match 1, match 2 in matches, if match 1 distance is less than, we'll say 70% of match 2 distance, whoops, and you can play around with 75% as well if you wanted to. Then we'll take the good list and we'll append match 1 to it. Okay, so we'll run that. Now we have our good matches. Now it's time to draw them. We'll say FLAN underscore matches is equal to CV2 draw matches KNN, k nearest neighbors, just like before. Pass in recess and key points 1, pass in serials and key point 2, then say good. There's no mask here, and say flags. And you can set flags either to 0 or 2. We'll show you the changes between those two right now. we'll say display flan matches. And if you run with flags equal to 0, what it's going to do is it's going to show you all the features it's matched on, except only draw lines on the best ones here. Okay, or at least the ones it thinks that are good. If you only want to see those lines, you can set flags equal to 2, as we've been doing, and then you just get those lines themselves. Okay, so notice we get really similar results here as we did with the sift. And for a really large image, this flan matching would have been, or actually this line right here, this flan-based matcher would have been a bit faster when you were searching for the matches than the brute force method. Okay, so now let's show you a couple of extra parameters you can do for actually drawing a mask. So often what people like to do is they like to draw these lines in a specific color and then show all those dots from flag 0 as a different color. So you'll see these lines as green and then all those dots as red. So we can see where we have potential features to match on, but only see the connections that we're concerned with. And the way we can do that is by simply adding the following. We create a mask. So I'm going to actually rerun these cells. So we'll run this one again, create the new sift object, create the descriptors. I'm rerunning those flan parameters, rerunning flan here, rerunning matches. But then after that, I'm going to do Alt-Enter to insert a new cell. And this one will be called matches mask. And this is going to create a mask, and it's going to be a little bit of complex list comprehension, but all we're going to say is 0, 0 for I in range length of the number of matches. And we'll be using this matches mask and editing it as we go along. Okay, so there is our matches mask. And if we take a look at it, it's just a bunch of zeros right now in the length of matches. And what we're going to do is turn some of these on by changing them to 1, depending if we have a good match or not. So let me comment that out. Over here, back in this ratio test, what we'll say is I, and then we'll select this as just a single tuple, so write those parentheses around it, and then we will enumerate matches here. That way we can actually keep track of the index marker. And then what we'll say is for I in match 1, match 2, and enumerate matches. We'll keep doing this right here, but then we will also say the following. And actually, we no longer need good here because the matches mask will do that for us. So we can get rid of good, and instead what we're building out is a mask. So we'll say matches mask at index I. So for that particular pair of 0, 0, change it to 1, 0. And essentially what that is going to do is it's going to label these lines as 1 where we actually have a good match. So all we're doing is we have this giant list of zeros, and instead of appending things to a good list, now we're just keeping track with indices of this mask of where we had a good match. So really similar process. Go ahead and run that. And now we're going to be using this mask to create a drawing parameter dictionary. We will say draw params is equal to dictionary, and we'll specify that the color of a match is green. So this is the color of the line. And then the single points that we saw, basically all these single points, we're going to color them something else. We'll say single point color, and you have to make sure your spelling is correct on this. We'll make those red. And then the next thing we're going to do is say pass in the matches mask. And this actually then defines where we had a match and where we just have a single point. Because remember, now it's essentially a list of 1s and 0s where we happen to have a good match due to that ratio test. And now we'll set flags equal to 0 because 0 flags actually shows all these little points. And then when we come back down here to draw this, after I run this dictionary, I'm going to get rid of good and instead pass in all my matches. So now all my matches, remember, if we take a look at that parameter, all my matches, those are both sets of matches of k equal to 2. What I'm going to do is instead of appending them to a list of good, I will be using this match mask along with the drawing parameters to filter them out based off color. So we'll still say none here, and instead for flags, we'll say 2 asterisks and say draw params. And you should see something that results like this. And all this is doing is it's taking these drawing parameters to color where you actually have the good matches versus where you have all these other points from flags equal to 0. And again, if you wanted to, you could just change flags equal to 2 to just see these lines by themselves. But often people want to color these just so they can see the relationship between the actual points. And all this is doing again is we're creating this mask object here. And from that, we're creating these drawing parameters where we say color matches green and then color single points red. And if you want, you can then play around with these values. You can turn this maybe into 0 and make this blue. And if we were to run this again, now you see the lines are blue. Okay, so this is the match color and this is the single point color. And you need to pass in the mask. And we say flags is 0, that way we actually see the points. I believe if you were to change this back to 2, then you would only see the lines. And there it is. So not much point in doing this whole dictionary if you're only going to say flags equal to 2, besides just setting up the color. All right, that's it for this feature matching lecture. You can definitely check out the resources if you're interested more in the details about the actual algorithms behind this OpenCV calls. In general, we'll just be making the syntax calls necessary to match features, and we're going to be building off of this when it becomes time to talk about object detection and object tracking in general. All right, I will see you at the next lecture where we discuss the watershed algorithm for image segmentation.